So let's do an example based on the binomial distribution. And I'll type out the prompt real quick. We have 5 road graders, just some equipment used in a highway construction project. They each have an operational life of T. We'll say, is that hours? That's hours. That follows a log normal distribution. Okay, and then the mean lifespan, and this is like, before they break down, you have to service them or something like that, we'll say. Mean lifespan is 1,500 hours. And the coefficient of variation is 30%. So this is a little bit of a new way to think about it. And we'll of course explore that. And so we're going to do we're going to ask a few questions. The first question we're going to ask is we're going to find the probability that 2 of the 5 machines will malfunction within 900 hours. So we've got these machines, we kind of know the specs on them. They typically operate 1,500 hours until they need some sort of servicing, maintenance, overhaul, whatever. And maybe it's critical for our projects that we have at least 3 operational more than 900 hours, right? So two fail or need maintenance of the 5 within 900 hours. All right, so there's a lot going on here. But first we'll answer this question, then we'll kind of explore some other probabilities. So I've given you the mean lifespan. I said T, and so this is going to be mu of T is equal to 1,500. And then CV of T is equal to 0.3. Now let's think a minute from really any problem like this, where we have a distribution, we need to calculate a probability of that from that distribution. What are the steps we need to take? Just take a minute to think about that, and then we'll talk about it. What do we need to find here? Kind of like the first thing we need to find, and then what are the steps we need to take to get there? Okay, so we need a standard deviation, but what else, and what is this going to give us once we have mean and standard deviation? Okay, we can do a z-score. Yeah. But there's another step before we can get to that. Do you remember that? Did you guys, so I don't know if we had time. I think we did this in class, where there's some special things we have to do to go from, this is mu of T and sigma of T, and ultimately we need, for the log normal distribution, we need mu and sigma of what? So remember, if T follows a log normal distribution, ln of T follows a normal distribution. But we don't have all the values, right? We just have a mean and a standard deviation of T. And so we need to calculate mu of Y and sigma of Y, where Y is equal to ln of T. And there are some special relationships that we use. And first, let's calculate sigma t, and then we'll kind of get into these steps. Ultimately, what this will do is we're going to get a probability, right? And that probability is that the machine will malfunction in less than 9 hours or 900 hours. And so that's going to be probability that t is less than or equal to 900 hours. So what is, first of all, what's the standard deviation of t? How do we find that? So what's the formula for this? Sigma t over mu t. Okay, so we can calculate that. So that's just going to equal mu t times CV. Okay, let's go ahead and do that. We get 450 hours. All right, so now we've got these two parameters. How do we get mu of y and sigma of y? Haley, do you remember? Can we just go ln of mu t? Can we do that? We can't do that. We can take the logs if we had the whole sample of data of t's. We could take the logs of those and then take the mean, but we don't have that. So we can't do that. There are two formulas that we'll use, and those formulas are based on what's called the method of moments. And moments are simply, mean, standard deviation, skewness. Those are moments. The method of moments says we can relate the parameters of the distribution that we're interested in to aspects of the data. And so the method of moments for the log-normal distribution says that we can calculate mu of y as ln of mu x minus 1/2 sigma y squared. And then for sigma y, that's going to be the square root of ln 1 plus sigma x over mu x. That's the coefficient of variation squared. All right, so we have the information we need to plug those numbers in. Let's go ahead and do that. But we have to do sigma y first. So we'll just plug in the coefficient of variation right there. So 0.3 squared. And then that ends up being 0.294. And then we can plug that in up here. So we get ln of 1500 minus 1/2 0.294 squared. If you calculate that, we get 7.27. So now that we have these, we can calculate the z-scores based on the kind of relationship between normal and log-normal distributions. And that relationship says that if, say, t follows a log-normal distribution, then ln of t follows a normal distribution, and then we can calculate the z-score this way. We say z is equal to ln of t, whatever t value we're interested in evaluating, minus mu y all over sigma y. So that's why we had to calculate these variables. In order to get this, standard normal variate, we need these parameters for the log normal distribution. And because we're interested in, remember, this is, if we plug this z value into phi, this is the cumulative distribution function for the log normal. Then the cumulative distribution function is the same as saying, what's the probability that t is less than or equal to some value? In this case, it's 900. So we'll just plug that in and we'll calculate a z-score. So we're going to say phi of whatever our z-score is. That's going to be ln of 900 minus mu of y. Divided by sigma y. So we get a negative z-score value. And I'll just draw this out from a log normal standpoint and then the standard normal. So we know that 900 comes before the mean. So the mean is going to be probably somewhere over here of 1500. And so we'll say 900 just over here. So we're trying to find this cumulative probability up to 900. And then now with the z-score, so we've got the normal distribution, a standard normal variate with 0 in the middle. And we're finding the probability up to negative 1.59. So that's from our table, or do you guys remember the function in R that does that? P norm. Yep, so P norm in R. So P is probability. This is the CDF function. And we would just plug in negative 1.59. Alternatively, we could do PL norm. So log normal. And we could plug in 900, and then we need mu of y, sigma y. So that's what we have to calculate those as well. And that gives us a value of I'll just write it out this way, phi of negative 1.59. If we look that up in our tables, we get 0.0559. And what's that the probability of? Just to remind ourselves. T is less than or equal to 900. Great. Okay. Wow. So that was a journey, and we're only halfway there. So now that we found our P, the original question was, we can go back to that, was find the probability that 2 of the 5 machines will fail within 900 hours. So now we're going to get to our binomial part of this. And let's just write in our so this is, we're saying probability that 2 out of 5 fail. And can I write this as a PDF or a CDF? Just take a minute to think about that. Two out of 5. We'll write this again. This is so my x here. So for the binomial distribution, we have, I think it's just y and n that the factors are. So y is equal to 2, things happening, right? In this case, failure is success, right? Success just means something happens. It happens or it doesn't happen. In this case, the machines break down, so that happens. So y is equal to 2, and then n is equal to 5. So because we're not thinking, is it up to 2, or is it greater than 2, right? It's just 2 out of 5. So this is probably that x is equal to 2, n is equal to 5. So then because we're saying equals, we can use what's called the, in this case, it's PMF because it's a discrete function. So we go to that, and that formula was n choose y, p to the y, 1 minus p to the n minus y. So the only hard part of this is saying, okay, what kind of binomial distribution function am I using here? Is it a PMF or a CDF, and how do I do that? So in this case, we said we're just saying exactly 2, so it's equal to that before we can use the PMF, and then we're going to go ahead and plug our numbers in. So 5, choose 2. How many different ways can 2 machines fail out of this series of 5? Times our probability of failure, so 0.0559 to the 2. That's 1 minus 0.0559 to the 5 minus 2. So go ahead and plug that in. Just get some practice using that NCR key. Something like that. It's just not the P1. The P1 is going to give you a much bigger number because that counts the order. And we don't care the order at which they fail. We just care how many different ways they can fail. So this is combinations. So I get about 0.0268, or we'll say 3%. We're not tracking sig figs in this class necessarily. So, what's the number that you want to report to your contractor or your project manager? We have a 3% chance of this happening. So in R, we can do it this way. D binom, so D for density. And the arguments for this are X, or I should write that as Y because we're kind of treating this as Y. So Y, how many, what are you interested in? In this case, that was 2, N, and then P. So the D binom 2, 5, 0.0. Let's just do 2 other quick things off of this. What's the probability that at least 1 malfunctions in 900 hours? So take a few seconds to write out this in terms of probability. What are we asking here? Probability that, we'll say Y, or sorry, yeah, Y. Y is the number of successes and failures, right? Probably that Y at least 1. So it's 1, it could be 2, it could be 3, it could be 4. So Y is greater than or equal to 1. And would this be a PDF or a CDF, a PMF or a CDF? So Sam knows. Okay, so when you see these inequalities, your brain should think, oh, CDF, right? Because it's a CDF is really less than or equal to. That's what it gives you, but you can do the complement. But what Sam said is this also equals 1 minus probability that y is equal to 0. So it's everything above that. So whenever we have a 1, we could just say, well, it's a discrete function, and so it's just anything that's not 0. So we can just take the complement of this, and this is the PMF is easier to solve because the CDF is a summation, and we have to do a bunch of calculations. So that's a shortcut. We could also write this out. So this would be the PMF. We could also write this out as 1 minus the probability that y is less than 1, but that ends up being, because it's discrete, probability that y is equal to 0. Because we can't, there's not like this continuous function up to 1. It's just, is it 1? No, then it's 0. So we'll do an actual CDF after this one. Okay, so this one's not too bad. Why don't you guys use your formula and write this out, and then I'll do it in a second. Let's write out the formula for this. And if you plug that in your calculator, and let's get some more practice with n choose r, we end up with 0.264, or about, we'll just say 26%. All right, one more example. Don't want to beat this thing too much, but we got to get a CDF up in here, you know? What is the probability that no more than 2 malfunction within 900 hours? All right, as before, take a few seconds to write out this probability. So no more than 2, so that's the same as less than or equal to 2. We can have 2 fail, but we don't want any more. And then now, in this case, now that we're at 2, we've got, you know, a few things to consider here. So we are gonna, this is gonna be a CDF, like we said before. And the function for that is just summing up the PDFs, because for a discrete variable, the CDF is just summing up the probabilities of everything up to a certain point. So we'll be summing up k is equal to 0 up to 2. And then we say 5, choose k, p to the k, 1 minus p to the n minus k. And the reason I'm using k as a variable is because that's what's going to be changing. It goes 0, 1, 2. So take a minute to write this out, and this is just going to be 3 of the PDFs for each of these points. Or PMF. And then if we plug all that in, we can do, we get 0.998. So a very high probability that no more than 2 will malfunction. And we can use our P binomial here. So this is the CDF function, and it'll do that summation for you. Always good to check in R, or you can just do it straight in R. I don't care. Note that you won't have R on an exam, so just keep that in mind. It's always good to kind of practice these functions. Okay. And this will give you the same result, the cumulative probability up to that value. Yeah, questions?
This last video question assignment, I was having trouble getting that function.
P binomial?